Today is the 6th of November. This is our sixth webinar with the speaker, Mr. Nishant Sharma and Dr. Jimmy Chandra. So I will introduce the first speakers for the first session in today's webinar. Mr. Nishant Sharma, graduate from Bachelor of Technology in Civil Engineering from IIT Kanpur and Master of Technology Structural Engineering from IIT Delhi. Is the General Manager of Elematic India Private Limited, having a total of 12 years of experience and is heading a team responsible for structural design and beam services for precast and cast in situ and steel project. He had delivered wide range of project types, including residential, offices, commercials. He specialized in structural engineering, earthquake engineering, beam, Revit, Tekla, component modeling, templates, automation. And then his area of interest include software intelligent development, automation through programming to achieve speed with accuracy in both design and 3D modeling. Mr. Nishant Sharma, if you have, yeah, okay. I think we see, okay, you have been spotlighted. So yes, the time is yours. You can give your speech for about 45 minutes plus minus, and then after that we will go to the discussion session. You still mute.
Sorry,
okay.
Sorry. Yeah, hello everyone. Yeah. So yeah, greetings of the day to all the members, all the audience. Warm welcome to the sixth webinar in the series. I hope you are getting a lot to learn, and you will continuously be getting more. And through this session, I will be able to give you some amount of knowledge to help you in precast connections design. So as Antoni introduced, I'm Nishant, working in the capacity of general manager. As a general manager, I have been involved in the number of projects throughout my career, like industrial, residential, and commercial. And what I'm going to present over here is the precast connections, which I have been using in all these projects. So shortly, I'll be presenting them. Some of them have been already executed, and some are in the process of being execution. So I'm going to start with the webinar. I firstly would like to thank the organizers, Rieckermann, for giving me this platform to share, as well as I would like to thank Elematic, my superiors who had chosen me to share, and obviously all the audience to be listening to my presentation. With this, I will start to share my screen. Yes, I hope my screen is visible to everyone. Okay. So precast connections actually form the very basic core of all the connections, all the core of fundamental of all the precast engineering technology, basically. So to come into the precast connection, I'll quickly give a brief of Elematic company. It was founded in 1959, and the head office is in Nacka, Finland. It is majorly into the supplying of the and manufacturing of Elematic machineries, which are crucial for creating all the precast elements. So the famous Elematic machineries come from this. It is designed in Finland and then goes across. It has production units in both Finland, India, and China. The customer services representatives are in UAE, Finland, USA. We have subsidiary offices and sales offices in UAE, USA, and various other areas. And representatives are over there in over 50 countries. With this small introduction, I'll just also give a small introduction about my department. So this is a basically design team which I'm leading, where I have expert team of structural engineers and BIM modelers, building information modeling. And the major experience that we have is in terms of design of precast as well as cast in situ and steel structures from all the types of structures, industrial, as I mentioned, commercial, and from low rise to high rise. And we are very much confident in different codes like IS, ACI, European, New Zealand, and British standards. So as a design team, the services that we provide to our customers are precast designs. We do the high-rise building design. We do feasibility studies. We do various calculations and quick cost analysis. We do pre-stressed concrete design. We have building information modeling disciplines of all the disciplines, not only structures, but architecture, MEP, as well as the 4D and 5D sequencing is also done. So that was basically the construction management through BIM. That is also some services that we provide. Project management is also through BIM is what we provide. Then we have QS, quality, all the quantities that we provide. As you can see on the lower right corner, this is a snapshot from one of the models that we have. So here we model all the reinforcements that is coming at the junctions and see. And this snapshot shows the engineering basically that we do with respect to the tall structures design. As a software, we are proficient in different analysis softwares like ETABS, SAFE, SAP, StatPro, SAP, and Concise Beam. For building information modeling, we utilize tools like, but not limited to, Tekla, Revit, Civil 3D. Okay, so starting with the precast connections. So as I told you, precast connections definitely forms the very integral and important part of all the precast buildings, because precast connections ensures that all the elements of the precast which is casted on ground and then erected at site behaves together and does not fall off from each other. So depending upon the intended purpose of the precast connections, we can categorize the precast connections into different types. So the basic category of the precast connection is between the dry connections and the wet connections. Now, the difference between the dry connection and the wet connection is that in the dry connection, there is no grouting or in situ concreting that is required to be done. You have embedded steel plates with anchor bolts, which is coming out. And the other precast column is also having the same steel plate, which is having the anchor bolts coming out. And then you simply on site, you just connect them using a in situ steel plate with anchor rods. So this type of connections is fast, but obviously it does not behave in the same way as similar to the cast in situ structure. So that comes to the wet connections. The wet connections is where the grouting and in situ concreting is required to be done. So all the precast elements of the floor, for example, you have beams, you have slabs, you have staircases. So each type of element should be interconnected with each other. Now that interconnection is done using a common wet joint that we call as a topping, which is placed on top of all these elements. and it gets connected to all the reinforcements are projected into the topping so that they are interconnected. So this is another way of connecting. Obviously, I'm not saying that dry connection is not inefficient. Dry connection is also doing the same purpose. It is just that through the dry connection, you have the shear transfer is only that is happening. You can emulate as a structural engineering as a pin joint, where the elements are connected with each other, but there is no moment transfer happening from one member to the another member. Whereas here you have the possibility of moment transfer depending upon depending upon your reinforcement detailing that is going to come in the topping area. So the wet connection can be further divided into as an emulative connection and non-emulative connection. When I say emulative, it means that if I have the same building which is done in a cast in situ, completely as a cast in situ, not having any precast element, having the same member sizes, the behavior of both the buildings will behave is the same. So that is the emulative buildings, emulative detailing. So my emulative connections, building having an emulative precast connection and building having a cast in situ connection, the behavior of both these will be same. But in a non-emulative wet connection, even though you have done a wet topping over here, but still the purpose of the precast connection, as I told, is the pinned connection. It's the same as that of a dry connection. Of course, in the dry connections also, there are other types where you can also have some moment transfer also happening. So that kind of a detailing then requires in the steel to be done. Moving on to the next one, there are other types of categorization of precast connections also, depending upon the requirement of those precast connection or the exposure of the precast connections to the seismic waves. Because in the presence of the seismic connections, seismic forces, the forces are of reversal and cyclic nature. So the precast connections will be subjected to quick cyclic and quick reversal of the forces, which it should be able to withstand. So those are the connections of the seismic connections, which I will show you in a short while, the differences between them. And the other type of connections is the non-seismic connections. So non-seismic connections are the ones where the majorly purpose of the precast connection is to carry forward the gravity load, whether in the form of moment transfer or the shear transfer. Its purpose will be primarily limited to the gravity load, not the reversal cyclic loading. Okay, moving on to the next one. So here I'm starting with the connections part. I'll be showcasing all the connections, mostly all the connections that I have been using. And the way I have formulated this presentation is in three parts: commercial, residential, and industrial. So we will go category wise between all these different types and see what all types of connections are used in different types of scenarios. So here is one of the buildings that I'm doing, which is a tall structure. It is having a 50-story, 40-story structure. So the top 35 stories we are doing is in precast. So there, this commercial structure is majorly office, and here these are the type of the connections that is being utilized. If I will go into detail into each connection. So if you see the first connection, this connection, so here you have the perimeter beam is there, which is connected with your precast solid slab. So here, in order to ensure that the beam is successfully tied with successfully tied with the topping, we have projected the inside bar of the beam outside into the topping area, as well as one bar is going inside the precast solid slab. So the purpose I'll explain for all these is one is that definitely the beam has to be tied with the topping. All the precast element has to be tied with the topping and intertied with each other. So that is the advantage that I'm getting by doing this type of detailing. But your question might be that why am I using a mechanical coupler, which means that my bar is going to be like this and another bar is going to be like this, and I have a mechanical coupler over here. Once I install this, then another person will come and he will start placing these bars and twisting it inside the mechanical coupler, the same way as the connection shown below. So to answer this question, this is related to basically what we understand is when we are devising a connection, it is not only the end intent that should be in the designer's mind, but it should also be the production intent that comes over here. So whenever you are producing a non-pre-stressed kind of a beam, so normally what they have is a middle shutter is there, and then on the right side shutter you have blockout boxes. So these blockout boxes, once you start pouring the concrete and the concrete pours up to this point, so the beam takes its the intended shape is taken. So these blockout boxes cannot accommodate the reinforcement projecting out from inside of this. So that is the main purpose of providing the mechanical couplers. So these thought process should be in the mind of a designer even when he's doing the detailing for the first time for any project, to ensure that the production is quite smooth. Coming to the hollow core next connection, hollow core to hollow core connection. Here I would like to highlight the criticalities that are available over here. One is that you have this groove on both sides, which is very thin and narrow. The order of the distance over here is around 30 mm to 50 mm. So in order to fill this joint, it is important to have first of all an aggregate size of less than 10 mm so that it is well going inside. And secondly, we have also placed a 10 mm bar diameter at HCS to HCS junction. The purpose of the same is to ensure that whenever there is a differential loading, the hollow core on the right side which is loaded more than the left side, then naturally what will happen is that there will be a shear transfer that is required to happen in order to both these slabs to act together. So shear transfer has to happen through this joint. So therefore, the reinforcement as well as the aggregate size ensures that this capacity, shear capacity of this joint is strong enough such that the differential loading does not lead to differential settlement and failure of this joint. That is the reason why between hollow core to hollow core at a typical floor, you will normally require to have one reinforcement available over here, as well as a grout material or a topping material. We have used the same grade as that of the topping, it's just that it is filled inside with the aggregate size of less than 10 mm. Okay. Moving on to the next connection. So this is the type of the connections where this is a similar to the other one. It's just that this is here it was a pre-stressed precast solid slab, but here we have a hollow core slab. So in the hollow core slab, the advantage that we have is that it has got holes and a core can be cut up to a certain length to access the inside. So how we have done how we have integrated the hollow core slab with the above is by providing this reinforcement T10 bar, which is provided in every open slit. So each hollow core we have like 6-7 slits. So in one hollow core we will open 2 slits, and in each slit we will place this reinforcement which is going and bending upward along with this reinforcement. Then we have this perimeter ties reinforcement, progressive collapse reinforcement that we need to provide as per the code as well, and it helps in reducing the progressive collapse. And secondly, these two connections I've already explained in the previous slide. As you can also see, we have provided in this particular. We also need to see the erection sequence that should be kept in mind. That when you are placing the hollow core slab only on one side, there will be a tendency for this beam to twist when the topping has not yet been casted. In order to support that, we provide this particular props at every regular intervals when we are erecting the hollow core slab. Once the hollow core slabs are erected and the topping is placed and the topping gains the strength of 75%, then only these props are removed. This is to ensure that there is no twisting that is happening in the beam because it has not yet been designed to take, it has been designed to take the emulative behavior, that everything is acting as a together. It is acting like a casting situ element as a together. So this is an example of emulative detailing where we have taken care of the production needs, and then as an end result, we are getting the emulative behavior. Okay, coming to the this particular connection here, if you can see in between the hollow core slab, as I told in the last slide, we had a 10 dia bar. So that 10 dia bar is now continuously going inside the beam and then coming out through the same mechanical coupler assembly. So this is a kind of a coupler assembly which comes like, which would be manufactured like this, and it will be placed while doing the casting of the precast beam. So as I told you, even with the casting of the Pcas beam, we will have the block-out box like this. So this bar cannot be continuously played. We cannot have a kind of a sleeve. So either we can have a sleeve, so in which you have to, put it bar inside. So that is also one way of thinking. Or another way is you have provide this kind of a assembly while doing the casting, and the bar will be twisted inside. So basically, precast connections need not be, standard everywhere, but the intended purpose at the time of production, at the time of erection, and at the time of end result, those actually needs to be accounted for when designing the precast connection. But it need not be same for every designer. It's just that its intended purpose to be satisfied. Now coming to the below one, here you can see in the red, we have provided one reinforcement which is going into the one precast hollow core slab to the another precast hollow core slab on the other side. So here also the one core is open up to a certain length, and this bar is inserted coming on top of the beam and then going into the another hollow core slab. The purpose of this is once the topping is done and this area is completely filled, as you can see, the whole thing will act as a together, and there will not be any loss of seating possible at any later date, because this bar, which we call as a hanger bar, will automatically act in tension and will resist the movement of HCS in this and this direction in the event of earthquake. Here in the same project, we have a cantilever. The cantilever amount is roughly around 1.5 meter that you can see over here also. So through this, I would like to showcase how even we are able to take care of cantilever kind of a detailing through this through precast connections. So with respect to cantilever, as structural engineers may understand, the top reinforcement is very crucial. However, the bottom reinforcement also plays a very crucial role. So in precast scenario, what we will do is first we will have this particular slab which is put over here and supported on top of this supports at every regular interval. And this supports will ensure that once the monolithic behavior is achieved, once the emulative behavior is achieved, then these props can be removed. The same fundamental that I explained in the last slide. However, the other crucial items over here is, as you can see, the bottom bar is developed all the way to the back and then bent up. And this is to ensure that the seating is definitely proper. If the seating length is increased up to this point, and once the casting is done, it is going to act as a together. But in order for this cantilever slab to act together with the top reinforcement is also very crucial to have these shear connectors, which is playing a very important role over here. So these shear connectors, if I'll draw the front view, you have these bottom bars, which is going over there, which is coming out. Then on top of this, you have the shear connectors. So the shear connectors are like basically this. At every regular intervals, you will have this kind of a bar which is projected out. So this will be casted on your solid slab table, and those shear connectors are coming out. The purpose of them is to ensure that the horizontal interface shear that is developed over here as a result of both of them subjected to a bending moment, right? As a result of both the section subjected to the bending moment, there will be a interface shear that is going to be developed at this joint, and the interface shear failure would be a very damaging factor if since the monolithic behavior will be lost and the top reinforcement will not be able to help anymore. So in order that the top reinforcement is acting together with the bottom reinforcement, the interface shear should be proper. Now, some people make the top surface as a roughen, which can also be done as 5 mm roughness can be provided. But in order for this critical kind of a situation where we have the cantilever slab which is coming out, it is good enough to provide these shear connectors at every regular interval when you are doing the topping. So this way, both these elements will behave as a together, and there will be no chance of the failure. In the commercial structures, this is also another type of the structure which I would like to talk about. So if you see in the plan view, I'm coming back to the plan view for a second. So this is my hollow core, HCS 265, which is resting on this side and it is resting on this side. But my question is, what will happen on this particular side? Okay, so and what will happen on this side? When we are having a beam on this side and as well as on this side, the resting is not required over here because it is a one-way span. All my strands are spanning in this direction. So what should be the connection over here? So this is the connection that we have proposed over here. As you can see that here we have given a gap of 50 mm, which is going to be filled with the wet concrete by providing some stopper and providing the wet concrete so that a person standing below will see a smooth surface. Okay, but the gap of 50 mm could have been a connection where we would have taken it on top of it. But we don't want to take these type of connections. The problem with this type of connection is all your main strands are going to be in perpendicular direction, in this particular direction only. But there is no reinforcement in the Pcas slab in horizontal direction. So what will happen is if you stop this particular edge, and this particular edge is a little bit free to deform because here you have another, so together they will deform like this, they will start deforming. So this particular edge will go down, but this particular edge will remain up. So there is chances of creating of bending moment stresses in this particular direction. However, since we have not provided any reinforcement in X direction, it is not good to have this type of connections where you have supporting the hollow core slab on one side on the beam. So if you see the casting situ slab edge reinforcement, which is given in New Zealand 3101, they are providing this gap of 600 mm to be done in the only as a topping. So this is the same theory behind this. But only thing is that this could be a good solution when we are having a false ceiling below it, so that it doesn't look awkward to any observer below that could raise a question or concern of structural problems. So if we are not having false ceiling below, so we provided this type of connection where 50 mm 50 mm gap was given. Okay. So coming to the commercial, we have the staircase also. Staircase connections are also there. Where the staircase connection we have is a 300. You can see the staircase is coming and resting on the floor landing. So floor landing, this is a floor landing. This is also a floor landing. And then your staircase is coming on top and resting on this. So the point to note over here is if you see that one edge is 305 and another edge is 300. So how it is to be designed, what considerations we gave into design, I'll let you know. One is definitely somebody who is looking from below should see a very smooth surface. So that was one consideration. Second consideration, that was a consideration for here as well. And the second consideration was that it is going to be casted in a mold kind of a scenario. So this is how the mold is going to be in the factory. And same is going to be over here also. Each mold is having a like 300 width and 150 as a riser and tread. So this during production also something that needs to be accounted for. So that is what led us to create the connection considering 300 over here as the last step where the jointing has to be done. So we have to take 300 over here because the mold is going to come like this. We cannot go further than this. But in this particular scenario, as you can see, we have the flexibility of going ahead. So that is why we provided the this X additional. So that both the purpose of having a smooth finish from below is also resolved, as well as production is also, it is production friendly. Quickly moving on to next. So this is an example of a seismic connection and a non-seismic connection that you have. On the left side, we have a column beam wherein the bottom bar is projected from below and added to it through a sliding coupler. So the coupler is placed here and it slides to one side. The other precast element comes from down and then it goes back to its place, and then we grout this. So the advantage of providing the coupler is definitely it is going to help you have a larger production efficiency of your factory, because the length of the beam that is going to be utilized in the length of the mold that is going to be utilized for creating one beam will be lower. Also, a point to note over here is that the dowel is going to come inside your dowel tube. So the dowel tube during erection should not be very close to the surface of this. So in order to protect the dowel tube, we have two stirrups, which is on the outside of the dowel tube, that is to protect the dowel tube from coming out. Secondly, as well as we also provided these shear keys, as you can see, as a good practice for this joint to behave together with this particular beam. So the idea is that this beam should be, this is an example of an emulative behavior where your beam is actually participating in seismic behavior. So all the top reinforcement and the bottom reinforcement is continuous, and the joint reinforcement is as per ductile detailing. But in the case of the pinned support, here on the right side, we are the column is like this, and the beam is like pinned on both sides. So it is just taking on the gravity load from the top. So here you can see the bottom reinforcement is not continuous, and even the top reinforcement will stop over here, and we'll have some connecting reinforcement as per the internal ties progressive collapse, which is provided on the topping. This is another example of a seismic and non-seismic connection. On the left side, you have the shear wall to wall connection. So this is a wall which has to act monolithic to the above wall. We are looking at the plan view, just for your knowledge. We are looking from the top of two walls. One wall is this and another wall is this, which has to act together with the wall in the another wall in the plan. So this connection call this connection as a stitch connection, where the bars, horizontal bars are lapped with each other. So LD plus 100 is the length of the stitch connection, and then we provide these ties on both sides to cover to compensate for the ties. But on the right side, as you can see, the importance of this particular connection, again plan to plan connection, and walls are connected through wire loop box. So the only role that this wire loop box is playing is the transfer of the shear, so that the wall do not have differential settlement. If one wall settles and the other wall is at this particular location, then there will be chances of formation of cracks, which we don't want. But at the same time, we don't want these two walls to behave together. So that is where this type of Pcas wide loop connection comes, which has a wide loop box, which is a kind of a box which inside which you have this kind of a wire, flexible wire. So somebody can just simply pull this off once it is installed. Once the element is casted, you can just simply pull this off. So then it will come and it will form like this. So this is what you can see over here also. It has come from both sides, and then a bar is placed inside together, looping these two, and then it will have. So the shear behavior happens because of the presence of this groove, as well as the concrete is, when the concreting is done, then the concrete flows inside this cavity also, which was created when the casting of the wall was being done. So effectively, your joint concrete, if in elevation, looks in this format, which helps in transfer of the shear as well. Quickly moving on to the next one. So this is the example of the commercial connections, where there are two types of connections, as you can see. In one case, on the left side, you have the main longitudinal bars are going continuous from below to above. So here, this type of connection in our tall structure, we are taking it in the lower stories, while above this type of connection, we are taking it in the above stories, where the reinforcement requirement is very low. So here we have bars which is stopping over here, and only the middle bar is continuing above. But here, if you have a vertical bar diameter of say 20 or 25 diameter, that is going to come over from top to bottom. So then replacing those with a single dowel will require a huge amount of bar and very low spacing, which we don't want. So here, the continuity of the bar becomes important in the lower stories, where the stresses are going to be very high in the walls. But in above floors, where the stresses are low and the reinforcement requirement is low in the wall, there we can go with a single layer of connections. There is another type of connections, wall-to-wall connections. Now we have come to the residential structures. So another type of connections that we have from wall-to-wall connections is these double tube connections, which are coming in circular, rectangular, and oval. Oval connections are also utilized for the scenarios where we want to have complete lapping from below to above from in the walls. So this is a 3D view that you can see over here, having these double tubes. With respect to the residential connections, this is an interesting connections where we are having a double wall system. So the wall over here is having an insulation in between. So heat insulation is there in between, and we have a double external facade over here and internal wall. So my main structural wall, which is participating in load transfer, is this wall, which is transferring it with respect to this wall, while this wall is only acting like a facade to this particular wall. But the advantage of providing this double wall is two. One is definitely the heat insulation because of the presence of the inner circulation. And secondly, the designing of the connections will give me this flexibility to have the double wall connection lower, while the above connection, the structural wall connection is above. So the advantage that you will get because of this is that even if there is a rainfall that is going to come over here, this wall surface becomes wet, the path of water to eventually come inside the floor is very difficult because it is against the gravity. So that advantage you get if you have this double wall kind of a system, which should also reflect in your detailing of precast connections. Same, if you can see on the right side, we have this is a floor system, and this was the balcony system. So in balcony, we have the facade all the way going up to down. which ensures the same water path becomes difficult, and it is adding another layer of safety to your waterproofing systems. This is the example of a solid slab acting like a cantilever. So here the solid slab is there, which is having a bottom reinforcement as well as projecting up, as well as the top reinforcement also projected into the development of LD. So here also you can see that what is happening is the precast cantilever slab is to be propped, obviously at the time of the, once the topping gains the strength, it has to be propped. So we prop this and we extend the bars up to 1.5 LD inside to act as it together with the topping, and then we can release the props. As I told that the connection's purpose has to be solved. It's not that the connection are going to be one type. So this is another type of the staircase connections where you have the same behavior being captured of a simply supported through steel resting on the solid slab. So you have this kind of assembly which is cast, which is placed inside when casting the staircase, and once it is laid, it is having the proper resting and so on. Similarly is the case over here. Now coming to the industrial structures. With respect to industrial structures, you will have definitely usually column beam structure or precast column structure. I'll come to that slide again. I'll just finish the column beam and beam connections. So here you can see the column beam connections. Sometimes you can need to require to provide a Dac type of connection. We call this as a Dac connection. Dac connection ensures that the look of the beam to any observer is that it is the same from below. The bottom surface is completely flushing. So in order to have that, you provide a corbel of approximately half the beam width, and half the beam width is acting like along with the beam, casted along with the beam. So the design of both the corbels as well as the beam dap is the same, where you provide this, and it is the same connection as we have shown in the staircase also, as you have seen in the staircase. So here also dowel is coming up and two stirrups we have placed on the left side, and so on and so forth. Equivalent of that is also given in the guidelines for the use of structural precast concrete in New Zealand Concrete Society, where they have created a steel, they have embedded a steel plate in the along with the precast concrete, along with the casting of the concrete, and then it is placed on top of your beam, provided with the proper supports, proper base for the steel plate. So coming to the column to foundation connection, these are the basic connections where we have this dowel tube connections, the bar coming from below into the dowel tube, which we have seen, and the mechanical connections. I'm sure you must be thinking that how these connections are going to behave in terms of earthquake. So I'll come to that point also later. But with respect to the column and foundation connections, there are a number of solutions also available that I'm going to present a few over here, depending upon the exposure that I have. So this is an example of a column shoe connection with the anchor bolt. So the anchor bolt is placed inside the footing when the footing is being casted, and the anchor bolt is projected up, and the column shoe is placed inside the column when the column is being casted. So these anchor bolts are then developed along with the main bars of the columns. So if you have a couple of more main bars, if you are thinking what happens if I have more main bars, then you have to provide a column shoe here as well, so that the bars are lapped. Or you can provide the equivalent number of column shoes depending upon the capacity that the column shoe is providing and the reinforcement arrangement that you have. But the lapping of bars is to be done. So this column shoe is being placed, and this is that type of a connection. This is another a connection that we developed as per the client's request, that he did not want to have a propping at the when the this is being casted, when the columns are being erected on top of the footing. He did not want any erection proppings. In order to avoid that, what we did is that we provided a temporary anchor bolt with a steel plate and the nut kind of a connection, which will be done at the time of the erection. And this base plate is part of the column itself. So the base plate is properly developed into the column through the reinforcement, and when the column is being casted, then the column is erected from the top into the anchor bolts. The nut is placed and the nuts are closed, and then we after doing the jointing over here, after doing the jointing and after doing the grouting from all sides for all the grouted sleeves, and the grout has also gained strength, then we can leave it. So this was the sequence, this was the alteration to the connection that we did to avoid the uses of props. This is another famous type of the connection which is very fast to execute or erect at site, is the pocket connection that we call it. So here also we have shim plates at the base of the pocket, which is coming from top of the foundation, it's forming the pedestal, and then we fill it with the grout, non-shrink grout on all sides after erecting the column. And then the further the SOG and everything is done. So the important question that must be coming in your mind, that what will happen in the seismic scenario in this particular things. So there has been various studies that has been done to acquire the behavior of these connections. One such study was done by Bellary and Riva, where they performed the cyclic loading test on the monolithic column foundation and the precast column pocket foundation. And similar studies have been done with respect to your dowel connections and coupler connections. And they have found that in all those connections, the behavior, if not improved, was at least similar to that of the monolithic column connections. So that is where we had the advantage. So it can definitely be said that if we are saying that the precast connections is not, it's incorrect to say that precast connections will not be able to sustain the cyclic loading, etc. Because the behavior of the structure is same as that of the monolithic, and in fact the performance is even better and more consistent rather than monolithic column foundation. At last, I would also like to explain about the building information modeling, the importance of building information modeling. As you can see, number of joints in the moment connection, number of bars come from either side of the beam into the joint. So it is important for building information to have the bars modeled accurately and checked that it is not clashing before you are giving out the shop drawing to the for casting. That way, what happens is that as you're doing the virtual construction in your computer, any clash you can accommodate quickly in your changes, and you can ensure that no clashes is happening at the joint while you are releasing it to site. Secondly, the advantage is also that you will get the output in the IML list, insert material list output that you will get, you can get accurately. These are the references that I have referred to. With this, the time is also short, I come to the conclusion of my presentation. I thank you very much for your patient listening.
Okay, thank you, Mr. Nishant Sharma, for the wonderful presentation. I think like the key of the precast construction is in the connection. So I think your presentation already shown very clearly what is the potential of the precast in the in the construction, and then from that
Yes.
we can learn so much that the structure can withstand also the seismic force beautifully, and then it can also control. We can also control the behavior of the structures. So with that conclusion, okay, we have one question from Mr. or Miss Melinda. Okay, I will. Please, you can ask the question. Mana sudah saya. Yes, you can unmute yourself, please. So if you have any question, just raise your hand and you can ask directly. In Indonesian is also okay. I will translate for you. Silakan bertanya, saya akan menerjemahkan dalam bahasa Inggris. Untuk yang mau bertanya, silakan. I think it's very clear what is the example for the connection. Ada yang mau diperjelas, silakan Bapak Ibu, if you have any question. Okay, I have one question from Mr. Liping Sang. If you want to ask directly, it's also good. So you just unmute yourself. I said it to be, you can unmute yourself. But if not, then I will ask, what is the minimum seating of hollow core slab? Note that in your double wall system, the minimum seating is 265 millimeter, while the HCS hollow core slab is 50 millimeter only. Maybe you can also see the question. If you have any comment, Mr. Nishant, about the seating of the hollow core slab, is there any code requirement for the seating?
Absolutely, absolutely. As per the New Zealand code, as well as in it is mentioned also in American code, the minimum seating that is required for hollow core slabs is L by 180. When the span of the hollow core slab is L, then the seating length required is minimum is L by 180, subjected to minimum of 50 mm. So L by 180 sometimes comes very low, but is subjected to minimum 50 mm. So that should become our design seating criteria. Once you have the design seating criteria, then you also add to it the account for the losses that can happen because of the imperfection in production of hollow core. The last edge of the hollow core might not be straight at everywhere, right? It can be a little bit deformed at other places. So how to accommodate that? In the 50 mm is your design, and then you can add a little bit more. So in my case, it was very less, and then the calculations for the losses was also very less. So that is why I took to 50 mm.
Okay, I think it's very clear. L per 180 for the minimum seating area. Okay, any more question? Please raise your hand and I will ask you to unmute. Kalau ada pertanyaan, Bapak Ibu silakan. Untuk Pak Pamuda, apakah mau bertanya? Silakan juga.
Okay, thank you, Mr. Nishant, for the presentation. Can you hear my voice?
Yeah, absolutely.
Okay, I'd like to ask about the connection of column and foundation, the pocket connection one. Is it only in the stage of research, or is it already accommodated in a certain code? The design, I mean.
Sorry, I could not understand your question clearly.
The design for the pocket connection between column and foundation, has it already been accommodated in a certain code?
In a certain code?
Is it already accommodated in maybe British standard, New Zealand, or
Okay. It is in American standard in Precast Concrete Institute, PCI. They have a particular chapter dedicated for pocket connection, as well as it is there in the Eurocode. In Eurocode 8 or Eurocode 2, they have described the various criteria that the pocket connection has to satisfy with respect to the transfer of the axial force, moment, and the shear force. How it has to be designed, these have been explained in PCI as well as in Eurocode.
Okay, thank you.
Welcome.
Okay, so for follow-up question, do you also use that kind of pocket connection in your project, Mr. Nishant?
Yes, in one of the projects, in the industrial project, it was to be executed very fast, and that is how we have come up with the pocket connections, and it was designed by us, and it was also executed according to the pocket connections.
Is
it
there
was
any
an industrial project.
Depth requirement for the pocket, like how much the
absolutely
depth?
Yeah.
Yes.
Absolutely. Since we are discussing, I'll quickly share the slide again.
Yes.
Yeah, so if you see over here, the length requirement is basically the amount of embedment that is required of the main bars inside the column into your this bar. So if I have the main bars over here, the main bars have to come inside the pedestal developed up till at least up to development length, plus if it is a ductile connection plus 10D. So how much development you want inside, that much embedment of the bar has to come inside, and therefore that much embedment has to be there inside the pocket.
Okay.
I think
So
also the thickness of the pocket, right?
The thickness of the pocket walls.
Yeah, it should be calculated also.
Yes, absolutely. The thickness of the pocket walls has to be calculated based on the type of the forces that is going to develop as a result of action of these moment connections. So when you have the value of P and you have M and then you have V, so what will happen is that this will translate into your local forces over here. So this is how they have explained also that it's to be designed. So you will have these forces which has to be calculated, and these forces will then be coming as a kind of a reaction into your pocket. So this wall should be able to take that much amount of shear. So this is how we design the pocket wall thicknesses. And since the moment is very high and this is the moment arm, so the base reaction over here is usually high. Therefore, normally you will find that the pocket wall thickness is very high at the lower end, but it reduces to a little lower value as we go up.
oh, okay. Okay, I think it's very clear. Okay, any other question, please? So we already like prepare a significant amount of time so that we can have this kind of session. So please don't shy to ask. And then this is especially important because the connection. I think if you have any question, please share your question and discussion. Silakan Bapak Ibu kalau ada. Oke, Pak Hari Nugraha, silakan Pak.
Ya, mungkin saya bahasa Indonesia aja Pak ya, biar
silakan. I will translate for you.
Mengenai sambungan dari mungkin antara komponen vertikal ya. Tadi kita lihat itu ada kayak angkur dari komponen bawah, kemudian masuk ke komponen atasnya lewat satu lubang ya. Dan kemudian itu saya lihat sih di grouting ya. Nah itu nge-groutingnya kalau saya lihat di detail itu dimasukkannya dari atas ya. Jadi cara gravitasi gitu. Ada beberapa pihak yang 100% tidak setuju dengan itu gitu. Jadi katanya harus dipompa selalu dari bawah sampai keluar dari atas. Gitu ya.
Oke,
dengan alasan pasti kalau dari atas ke bawah itu ada rongga yang tidak mungkin terhindarkan.
Baik, saya mengerti. Itu saja, Pak.
Ya intinya sih itulah.
Baik Pak, saya akan tanyakan. Okay, yes, Mr. Nishant, there's a question from Mr. Hari Nugraha. He asked about the connection for the vertical component, vertical element, when you have the anchorage using the connection, and then after that you grout. So how do you normally grout the component in the vertical element? Because like when we seen your slide, it was shown that the grouting is from top to bottom. Well, there is many engineers disagree with that method, because when you are grout from top, then it is certainly there's a pocket of air trapped inside the grout, and that is troublesome. So please share out about the connection, vertical connection. Maybe you can share also the screen is also.
Absolutely. Just a moment. Let me share screen and repeat the question so that if I understand correctly.
Yes.
This is regarding the this is regarding this particular grout. So the question is that is the process of grouting these grouted couplers? Is it such that there is
Yes.
no air that is left inside, right?
Yes. Yes. Normally, how do you do it? And because when from top to bottom, there is a disagreed from many person. So please share us your method.
Yeah, absolutely, absolutely. So the grouted coupler is basically the type of coupler that we have is basically this is my precast wall or column, and then this is the bar which is already fixed with the coupler, and the bar which is going to come from below is projected inside here once we lay inside. Now we have a tube which is coming to the surface at the below, and we have a tube which is coming on the surface at the higher level. So the process of putting the grout is not through this tube. This tube is only acting as an indicator. We always inject the grout with pressure at the below tube and wait for the grout to fill completely in the inside and ultimately appear in the top phase. So once it starts to appear in the top phase, we understand that the grout is completely filled, and then it is coming from the other side. So that is the how it is done. So it is injected through pump or pressure tubes into the lower bottom of the grout.
I see. Yes. So I think it's agreement because with this method, then you don't have any pocket of trap air. Is it the same for the thicker one, the seismic connection? And how about the other one, the one that you shown using the bolt connection? Well, from that side, it doesn't seem any hole in there. Maybe you can show us the other slide.
Middle one, this one.
No, the other slide. The other slide that you shown us the footing and then with the bolt connection.
Just a moment.
Yes, sorry.
Antoni, itu kan ada dua gambar tadi di slide.
Ya Pak, betul. Saya minta gambar satunya itu.
Yang sebelah kirinya kayaknya dari atas tuh masuknya.
Oh, ya, nanti akan saya informasikan lagi.
Nah, itu yang sebelah kiri.
Yes. Sorry, please return back to the previous picture, the first picture. Yeah, this one. One question is like, for the left picture, it seemed as is that the grout from top to bottom is still the same from the bottom to top, or just the air is still
no. Here it is from bottom to top to bottom, but here the available sleeve diameter is very high. It is, for example, 75 diameter sleeve is there. This is a corrugated sleeve which is of this shape.
Oh, okay.
This is of the either 75 diameter or 50 diameter, which is very high. So if you have this particular sleeve, your bar is going to be in the center. For example, this will be 20 diameter. So this definitely gives you enough space from all sides. So here, if you start
top to bottom.
Here it is always from top to bottom. So here, when you start pouring, it has got enough space to, and it will fill inside. And the corrugated sleeve, since it is having a groove inside it, so it automatically bonds with the concrete which is outside. I mean, this particular concrete, and it will also the grout which is going non-stream grout, which is having a very small aggregate size. That small aggregate size will also fill in that inside of that particular groove. So the shear connection between the grout and the corrugated tube is better from outside as well as in the inside. That is why we always use corrugated tube when we are providing.
Okay, so I think the conclusion is for the smaller hole, you always fill from the bottom to up.
Yeah.
But for the larger sleeve, you can use from top to bottom. With from the picture, we've seen that there is still a large space from the top of the rebar to the top of the hole. So we can ensure that the hole is the connection can be filled fully.
Absolutely.
Yes.
Absolutely.
So one question I have, like for the another picture that you show us the connection using the pole connection. Is this connection will be grouted also?
This
Yes,
connection?
this one. Yes. So for the bottom one, I see that you just tighten the screw, so it does not need any grouting from this type of connection.
No, this cannot be left exposed like this. Ultimately, you have to provide a shutter from all sides. You have to fix the shutter from all sides and then start pouring the grout from all sides.
Okay,
Or,
so just like a steel connection, we need to fill out all together.
Ultimately, it will be covered from all sides. It need not be grout. It can be a simple mortar as well. The purpose of the same will be such that this bolt and the nut is not exposed to the weather at the later stage.
I see. Yes.
So it will be same as this, as shown in here. You can see. Ultimately, this mortar fills this region completely, and because of that, what happens is that it is not exposed to the weather, and rusting will not happen.
Yes. Oke, supaya tidak terjadi korosi, semuanya harus ditutup. Baik, Bapak Ibu, Pak Hari, kalau misalnya ada, kalau sudah oke, silakan Bapak Ibu kalau ada yang lain yang mau bertanya. Anybody else, please give your question.
Moga-moga para engineer yang tidak bisa keluar dari pemikiran itu bisa paham sekarang lah ya.
Betul Pak, jadi dengan adanya koneksi ini akan sangat memperjelas. Jadi ini salah satu presentasi kuncinya supaya kita bisa dapatkan struktur Pcas yang bagus. Silakan Bapak Ibu, silakan. Any more question, please? Just raise your hand and I will translate for you, or you can just ask yourself. Very good discussion. Sudah berapa menit ini? Kira-kira sudah. Ya, we still have short time, not much, but okay. Pak Henry, silakan Pak kalau mau bertanya. Sorry, ya. Silakan. Sorry, Pak Henry masih mute. Oke, sudah.
Mr. Nishant, this kind of precast connection that you just present in India, how right this kind of precast connection has been applied to buildings, high-rise building as well as residential buildings, if any?
Yeah, in India, actually, we have now a lot of ingress of precast technology, and it is being widely adopted in especially in South India as well as in North India a little bit. But especially in South India, precast residential buildings are very widely adopted because of the repeatability and modularity that residential buildings present. So in these type of all these type of projects, these type of connections have been widely used because I have been involved in understanding what is the current precast standards while I'm designing for my own projects. So I have seen that it has been these type of connections, especially the wet connections, as I told, with respect to the topping, has been widely used in India. In European countries, mostly dry connections also comes into picture where the earthquake is not very prevalent. But here in India, since the earthquake becomes prevalent, so we always have this topping kind of system. So here, the connections that I have shown has been, very widely used. No doubt.
Thank you, Dr. Nishant.
Thank you. Thank you.
Okay, I think that is also good because we have some example from India with the seismic resistant design. And that is also give me some question also about the repairability of the connection. Have you any experience in the repair of the connection? And then is it more difficult or is it simpler rather than the cast in situ concrete? What do you think about it?
No, actually, I did not have any such experience where the precast connections has failed and then we have to repair. But what I understand from my understanding is that since we are designing most of the connections to behave in an emulative way, So once the connections has already been placed, it has been casted, the building is functioning, it is majorly same as that of the cast in situ. Now, if there is at the later date, if there is because of any failures, we see some kind of a cracks or some kind of error over there, damping over there, then we have to do the same retrofitting. I understand same retrofitting as that is done for the cast in situ.
I see. Yes, yes. Okay. Yeah, that is also clear. Because like when the building is already been erected, then the connection has been wet connection, and it's just the same as the in situ structure. So if there's earthquake, then there's also repair with the same prevalence. Also, okay, so we have a question from Mr. or Miss Sergio Negina. So what is the correct details for the precast stairs with no surrounding concrete walls in seismic regions? Stairs are very stiff and act as braces in a structure. They are not ductile and the detailing need to allow movement. So what is your experience in the designing the stairs in the seismic resistant structures? So if any provision given to the connection?
So basically, the question is definitely correct that since the staircase are not integral in seismic resistant, but still because of the bracing, they do provide some lateral stiffness to the walls to which they are connected to. So first is, as a structural engineer, we would keep those walls out of the seismic resistance by keeping them as a gravity wall when we are doing a design of the structure, so that they don't participate in earthquake. But if I have to utilize those walls in the earthquake, then the connection between the staircase and the precast wall, we will keep it as a pinned connection, not the fixed connection. So in that scenario, I'll share the slide again to better answer. I'll go to the staircase one. Yes. So as you can see in this particular connection, both the bottom and the top reinforcement is not continuous along the into the wall. So they, even after being casted, and there is no wet connection over here. This is kind of a dry connection. We are just placing and we are doing the grouting over here. That's it. So the bottom and top reinforcement is here. So this will not participate in the precast wall stresses, even though this is a shear wall structure. Now, further, as to answer your question about the movement part. So here we have taken the gap of 15 mm, but this can be seen with respect to the, and after the analysis as well, that how much sway is coming because of the participation of this particular wall in earthquake. That much amount of gap plus the minimum sitting rent, that much amount of corbel can be provided. But as you can see, after the gap is provided, still the main importance of this connection is that this should be a pinned connection, not a fixed connection. And the pinned connection is being provided through this type of connection.
Okay. So the short answer is yes, you still have to design it, and then design it carefully, because the stair will act as additional braces when it's fixed. So given the distance and just ensure the pin connection. Okay, thank you. Okay, another question. Do you think, from Mr. Christopher, do you think the precast system on the stair you described can be applied in the housing project in Indonesia effectively? In this case, do you craftsmen and workers need special skill or certification? I think, yeah, just give a comment on what is the application for the low-rise housing.
Yeah, I think it is absolutely, it is going to be absolutely efficient to apply in housing projects, especially because there the modularity of the staircases is very high. Same staircase scheme is utilized almost everywhere. So one precast mold which is serving for the staircase at one location can serve for create all the staircases at every location. Now, with respect to the skills requirement, if your craftsmen and the workers are skilled for precast connections, then I believe that they will be able to do this staircase connections as well, because staircase connections are no special, no different than other precast connections. So it can be definitely achieved. It is not impossible.
Okay, thank you. Yeah, maybe another 1 or 2 question, and then after that we can end the session. Silakan Bapak Ibu, mumpung ada kesempatan. Kalau ada hal-hal yang mau ditanyakan. Yeah, I think the example is we've seen many examples. Okay, so maybe one last question from me is about the challenges from starting for the use of precast in Indonesia. Maybe you can share us a bit like what is initial resistance to the precast industry to be accepted in India construction industry. Do you have any insight on that? Because we are still developing the system for Indonesia. Maybe we can learn from you also.
Basically, majorly has to do with the investment that the client is possibly trying to do, and how the challenges majorly is with respect to the return of the investment is what I have understood. Because you have to set up a factory and you have to then execute once the factory is in place, then all the projects has to be done such that the cost of setting up the factory has been break even. But as a challenge, if I tell you, setting up a factory is not a challenging. Having a skilled labor is also not a problem. It is only that we need to educate everyone that this kind of a problem is not there. It is only in our mind. And if you have a potential number of projects that is going in the pipeline that you have, then setting up a factory is going to be more economical. But obviously, you have to be educated for that. I mean, somebody needs to let you know for that. So that is where we face the challenge. We spread the word. We had various sessions, and that is how now many clients and many developers are now progressing towards adopting this precast technology. And once it gains momentum, then everybody starts to understand the advantages also. That is always there.
Okay, I think your summary is very, very important for us, because we also feel the resistance to move forward with the precast, and then this is our way of educating the potential engineer and then the customer also. So yes, thank you for your insight, and we hope that the precast industry in Indonesia can also be continuously improved. Yeah. Okay.
Absolutely.
Okay. Still one question maybe, and then this is the last one. How can we use splice sleeve connection in critical area of seismic resistant element? Critical area is where we expect plastic hinges from the seismic loads. So just the connection for the seismic resistant element. This is a question for the.
Yeah, I'll quickly reply to this. The question is definitely correct that the critical areas where we have seismic loads, there the formation of plastic hinge definitely is accounted for while doing the design, because the engineer always has some response reduction factor which accommodates this formation of this plastic hinge. So to answer this question, definitely that is the reason why I had added that particular slide where I had shown the comparison between the monolithic and the precast connection. So this is the kind of a splice connections that I had shown, and then further this graph was shown. So basically, if you see this graph, it is going into the plastic region every time, and then it is coming back, and then going back into the plastic region. So that experimental study on the splice connection has been done throughout this through by Bellery and Riva, and it was found that the behavior was very much similar. Secondly, if I talk in detail about the splice connection, I'll go back to that particular slide. Sorry. Yeah. If I talk about the splice connection, so basically plastic hinge is going to form over here. And if I have to have a monolithic bar would have been simple straight bar with the stirrups around it. That which you will agree, and it is replaced with this type of connection. So here this particular splice strength plays a role. So we as a structural engineer, we always define that what is the performance criteria for this coupler, and the performance requirement that we set for the vendors is that its capacity should be at least 1.25 times the capacity of the reinforcement bar. So so if you make this particular region is now stiff, but the bar is continuous, the bar is behaving continuous, is just that this particular region is now stiff. So any failure that is going to happen, it will happen outside the coupler region only. And outside the coupler region, you have the reinforcement bar, which is designed to be yielding when in the event of the earthquake. So that is where we ensure that the seismic, in the event of the seismic, the plastic hinge will be taken care without failure in the splice.
Okay, I think that is the key of the design. And when we design the connection, we always ensure that it can behave. It can behave more than the connection that we are trying to connect. So yeah, with that in mind, and then the comment from Mr. Chong Chung Eng, and coupler and splice sleeve are the bar break system. So what does it mean, bar break system? It should not break or what?
Yeah, I think he's acknowledging the answer where we have, I mentioned that the splice has to break only after the coupler, after the reinforcement. So reinforcement will break first.
Okay. Okay. With that comment, I think the connection should be stronger than the connecting part. So that is the main idea. And with that, we conclude the first session. So I give very much appreciation for Mr. Nishant Sharma. So
thank you, Antoni. Thank you, everyone.
Thank you for your wonderful presentation. Please stick around if you still have time. If not, then I will share your presentation with the audience later on, and we will also have the YouTube available later date. We will go to the second session, but before that, we will have like 5-minute break, I think. Yeah. So we will return at 14:30. So you can fill up your cup, stretch a bit, and then we will return for the second session with Dr. Jimmy Chandra. Thank you, everyone. Thank you. No.